Good evening, Lower Six. The next part of the course we're going to have a look at, now that you've finished density, is something that's quite simple. You will have covered it at GCSE, but obviously we extend it a little bit at A level, and that's Hooke's law, which basically describes how a material behaves under a force that is trying to extend it. Now, a force that's trying to extend something we call a tensile force. A force that's trying to contract something, we'd call that a compressional force. As far as Hooke's law is concerned, it does apply mostly to springs. At least that's where you will certainly see it being applied to most often. But in fact, it can be applied to a range of materials, including wires and other materials. However, you get a much bigger extension for a small force if you've got something like a spring, and also a spring obeys Hooke's law over quite a long range as well. Hooke's law was originally a empirical law. The person who discovered it was Robert Hooke, who was a contemporary of Newton, so quite a long time ago. And basically Hooke's law says something quite simple, which is that the extension that you get from a spring is directly proportional to the tensile force that is placed on the spring. So if you were to double the tensile force, you would double the extension. Be a little bit careful with the word extension of a spring. Extension of a spring doesn't mean the total length of a spring. It means the additional length of the spring beyond the point where there was no force acting on the spring. So if you look at this spring down here, it's actually about 2 centimeters long at the moment, but there's no force of no tensile force stretching it. If I was to extend this spring, okay, then the extension would be the additional length beyond 2 centimeters. So if it stretched to 6 centimeters, the extension would be 4 centimeters or 0.04 meters. So don't get confused by that. The extension is the additional length above the original length when there's no force on it. I would say as well that Hooke's law does also apply for compressional forces as well. It wouldn't apply in this case because we can't compress this particular spring, but some springs you can compress, and for those springs the distance of compression would also be proportional to the compressive force. Okay, so that's basically Hooke's law. Now, I'm going to show you, obviously under here, there's a graph, and I'm going to explain this graph because this is an important graph that you will have to learn at some point. So what we've got here is a graph that shows for a spring the extension along the x-axis against the force on the y-axis. So as you would expect, as you increase the force, the extension of the spring increases. Now, initially it obeys Hooke's law up to this point P, which means that for that range there, the relationship between force and extension is directly proportional, so a straight line through the origin. Now, we can write that as an equation. You can see the equation here, F equals K times delta L. Delta L is the extension, F is the force, K is the constant of proportionality. Now, that constant of proportionality is called the spring constant or the stiffness. The unit of it is newtons per metre. And the bigger the value of K, the stiffer the spring is. This spring here I know has a spring constant of about 26 newtons per metre. That doesn't mean you can stretch it for a metre, but if you carried on stretching it at the same rate with the same increase in force and it didn't break, then you would require 26 newtons to stretch it to an extension of 1 metre. Obviously that's impossible. So that brings us to what happens if you do stretch a spring too much. Well, eventually at some point it stops obeying Hooke's law. So I've labelled this point here on the graph P. And beyond point P, as you increase the force, the extension no longer increases in direct proportion. So the graph deviates from a straight line and starts to curve. There is then another point, which I've marked E, which is called the elastic limit. Now, quite often, especially at GCSE, students confuse the limit of proportionality and the elastic limit, and they are actually slightly different. The limit of proportionality is the point at which Hooke's law stops being obeyed, but the elastic limit is the point beyond which the spring will not return to its original length if the force is taken off. So in fact, I've got two springs here, and they are identical springs, but you can see quite clearly that the spring down here has been at some point extended beyond its elastic limit, because when the force was taken off, it didn't go back to its original side. It's been permanently deformed. Okay, there is another word for that, which is plastic deformation. So up to point E, we have elastic deformation, which means it basically, if you take the force off, it just goes back to its original length. Beyond point E, you have plastic deformation, where if you stretch it beyond there, it won't go back to its original length. So if we were to take it up to this point here, and then we took the force off, rather than going back down here to here, it would drop back down to about here. Okay, and it would stay with a permanent extension. So that's what we mean by limit of proportionality and elastic limit. Now, they're normally fairly close together, especially for a metal spring, but for different materials, they may be further apart. Okay, eventually as well, if you do take it much further beyond the elastic limit, it will get to a point where you're increasing the force and the extension increases massively, and then it finally breaks at some point as well. So that's a curve you would get for a spring if you were to carry on increasing the force and measuring the extension that you get. The next thing I'm going to show you is just experimentally how you would actually do this experiment and get this graph. Obviously, if we're in school and we're in the lab, I'd be getting you guys to do this, hopefully better than how you did it at GCSE, and more accurately, and thinking about your errors. So I've got the setup here. So this is basically it. So I've set it up on a retort stand. So I've got a spring being suspended from a clamp, and I've also got a ruler that's suspended here as well from another clamp at the bottom. Now, what we've got to measure for different forces pulling on this spring is the extension. So what I've done is I've set up the ruler so that it's the zero on the ruler should be exactly lined up with the bottom of the spring. Now, if you're doing this carefully, you do have to take a few precautions that you probably wouldn't have thought about at GCSE. One of them is making sure that the ruler is perfectly vertical. Now, one piece of equipment I've got here at home is a plumb line. So let me just get that. A plumb line is just a lead ball on a piece of string. So if I hold that next to the ruler, you can see that the ruler has been set up perfectly vertically. The other thing that I've got is a set square, and using the set square, we can hold the set square here and just show that actually it is lined up with the zero. So then when I put a weight on here, I'm going to use a weight to extend the spring. All I need to do is then measure the length from the ruler, and it should always be to the bottom of the spring, so I'm not including the loop at the bottom. So that's what I'm going to do. So what I've got here are some masses. So I'm going to put the masses on. So if I pull back here, okay, so that's the experiment. Now, if you're doing the experiment fully, you would change the masses. So you'd start off with 100 grams, go 200 grams, 300 grams. In fact, with these springs, you can go up to about 700 grams before you would damage the spring. Okay, at the moment it's got 300 grams on, so that's 0.3 kilograms. Multiply that by 9.8 newtons per kilogram by G, and you get the force that's pulling down. So 0.3 times 9.8 gives you, I think that's 2.94 newtons. Is that right? 2.94 newtons. So you know what the force is, and then the only other thing then is to measure the extension. So one thing that you do have to be careful of in an experiment like this is parallax error. Now, parallax error basically means that you're taking the measurement from the wrong angle. You're lining something up with a scale and you're not looking at it perpendicular. So if I was to take, I'm representing the camera with by my eyes here. If I was to hold the camera here at a funny angle, obviously there's the bottom of the spring. If I was to line it up with the ruler there, I would get a very dodgy result. So what you've got to make sure that you do is take your eyes and line it up at right angles to the ruler. Okay, and the other thing I've got here to help me is a set square. So what I'm going to do here is, once it stops bouncing about, so there we go, stop the spring bouncing, is I'm going to make sure that the ruler is at right angles and I'm reading off as best as I can. It looks like 115 millimeters. So obviously on my table I would write down 2.94 newtons for the force and 115 millimeters, or 0.115 meters for the extension. I then go and get another weight. So here we go. So I've got another weight there. I'll put another weight on. And you can see that the spring's extended. Okay, and I would carry on up until well, before the elastic limit. I don't want to go beyond the elastic limit, otherwise I damage my spring. And so you'll get a table of force against extension. You then plot a graph, and that's the graph you should get, okay, at least from here up until there. Okay, so that's basically it. So what we're going to do is we're going to give you a few notes to write down. We're also going to give you a little homework sheet to do. And it's Saturday at the moment, so hopefully I would like you to get this in by Tuesday morning. Okay. I didn't give you anything last week, so we need to start catching up a bit and making sure we get through the rest of the syllabus. Okay, thank you very much. Don't forget to ask any questions if you need any help.